question, is moisture in the air good or bad? Is there somebody needs to go on mute? I think we're hearing a little feedback. Okay, we'll try that. I always ask the question, is moisture good or bad? And the answer is yes. Moisture tends to be good for the people. That is, we kind of like moisture levels at 35 to 55 from our skin, our nasal passages, but our buildings hate that, especially in cold weather. We get condensation. So we want the relative humidity in the right range so that it's good for the people, and also okay for the building. And so that's where we're going to head with this when we talk about moisture. I always like to show this building. This is my neighbor's building in Southampton, Ontario, just off Lake Huron. This building was built in 1886, about 100 years ago. Somebody slathered stucco over it. Pretty simple box house, right? And I would say, did this building work? Does it show any signs of moisture issues? And the answer is, yeah, lots of moisture issues. My neighbor, he's a school teacher, he would still say it leaks now and again. But notice it's just the stucco that's damaged. See if I have a shot of it after the fact. Just a second. I don't have a shot of it after the fact. But when they took the stucco off, it's actually in reasonable shape. Some of the boards underneath the windows are gone, but there's no structural damage to the house. And the reason this house worked is it got wet, but it was able to get dry. This is a big issue for, well, everybody on this call. You're living in cold climates, most of you, cold climates. Buildings get wet throughout the throughout the fall, winter, spring. They get wet, but when we didn't used to insulate buildings, you had the furnace going or the oil furnace or an old wood stove, and the building was able to get dry. The big difference we now have is the issue or the interest in better insulation of buildings. So the minute, and my neighbor said to me, so what should I do this house? I said, well, if you're going to insulate it, because it wasn't insulated at all, if you're going to insulate it and turn it into a year-round building, you first have to fix those water issues on the outside, and then you're going to have to manage moisture on the inside. So keep that in mind in all of your communities. We'll often hear this, well, houses used to work better. They don't build in the way they used to. And it was mainly the drying potential. Try to keep that in mind. It's the ability for buildings to dry. And the more insulation you put in walls, and I'm not saying don't put insulation in walls or attics, just understand the more insulation you put in walls and attics, the more concerned you have to be about water management. So hopefully that's useful. And here's why. More insulation does two things. Heat, it stops the flow of heat. And heat is obviously you're paying for the energy, but heat also is good at getting things dry. So when you insulate, you stop the flow of heat, which stops the drying potential. It also makes surfaces colder. That is, the more you insulate this attic, the colder the underside of the roof deck gets, the colder that sheathing gets. So if there is any moisture in the attic, it condenses. So insulation makes it colder and stops the flow of heat, so you don't have any drying potential and you have more wetting potential. And of course, we are making buildings more airtight, which is a good thing. It stops, when I make buildings more airtight, it stops warm, moist air from the house getting into the attic. That's a good thing. But now that moisture stays in the building, and we have less drying potential in that building. So we have less ventilation, less drying potential. Even though we don't want the moisture leaks into the walls, we do need to understand that more more air tightness reduces drying potential. And then for the most part, we're building out of materials that are more sensitive to water. OSB and plywoods are more sensitive to water than, say, the traditional solid wood components. Wood itself, of course, is susceptible to moisture, but a solid piece of wood would have to be wet for weeks before we'd have to worry about it. OSB would have to be wet for a matter of days before we'd have to be worried about it. So three things happening. We have more wetting potential. Notice this building on the right-hand side here. This is a building that's 1.5 years old, and it's already leaking. Notice the guy at the bottom left is spraying this wall with water. That water ends up inside the building within 20 minutes of spraying the outside. That has to do with cladding systems and so on. And the OSB is already showing signs of damage after less than 1.5 years. So we have more wetting potential, and we have more insulation, which means we have less drawing potential and we have more sensitive materials. So that's just sort of a backdrop, or at least an introduction to the topic. And then
We need to have you advance to at least slide number 4. Right now, we're still seeing your I guess title slide.
what?
There you go.
We got it now.
Well, so it's not allowing me to advance my slides. Okay, so I'm gonna have to do it this way. Sorry.
Okay.
Yeah, my apologies. So that's gonna make a mess. But anyway, okay. So so there you have it. You know what's changed. Now you're seeing that building. God, sorry.
Oh yeah, this makes sense now.
Now it makes sense. Jeez, I wish.
Boy, this guy's pulling rabbits out of his hat. I like it.
Oh, we clearly didn't practice. My apologies. That's my fault. I guess we'll know for the next what I'm doing, right, John? Okay. So, so this building. So I won't go back. I'll just keep going forward. Okay. So what I wanted to get to then is understanding moisture, and you guys will all recognize moisture comes in 3 forms: solid, liquid, vapor. Right? Solid being snow and ice. Liquid water flow, and then gas or vapor form, humidity. And all 3 of these are important, but we're only really worried about moisture when it gets into liquid form. That is, we don't really care what the relative humidity is in a house until we start seeing condensation. You'll notice that top picture there, condensation on the window is really important to us because that liquid water starts creating damage inside of our buildings. So keep that in mind. And then when I said, is moisture good or bad? On the left-hand side, it's good for comfort, good for health, good for furnishings and finishings, but condensation, mold, health issues, and sometimes it degrades finishings and furnishings as well. So good for the people, bad for the building. This is a really old slide, but it was actually just validated because of some COVID research. This is the optimum humidity range, and we've taught this in First Nations communities for years. Gail Lawler, Tex McLeod, myself, CMHC taught it, Health Canada teaches it, that 40 to 60% range is really good. Notice the second bar down, viruses really tend to not propagate very well in 40 to 60. But you guys will recognize at 40% RH in the far north or anywhere in Canada, frankly, at 40% RH in the winter, you're going to get condensation on windows. So we tend to need to be lower than 40, but as close to 40 as we can get. And then in the summer, try to keep it low as possible. So here's the range. This should be important to you. This is the range that all of your communities should strive to be at. You should strive, and well, I'm going to take it, that third coast, the far north coast, you need to be lower than this. But for the most part, most communities, in the summer, you'd like to be at 50% plus or minus 5. In the winter, you'd like to be at 35% plus or minus 5, maybe as low as 25. The real watchword is this: if you go into a house where there's excessive condensation on the windows, not like a half an inch of moisture, but enough moisture that it's dripping onto the sill, damaging the sill, that's too much moisture. And therefore, you're going to want it to get lower than that in order to get there, but to get rid of that condensation. But that should help you 35% plus or minus 5 in the winter. It's a pretty important number. And I just want to remind you the concept of relative humidity. Relative humidity is a measure of how much moisture is in the air compared to how much that air could hold at any given temperature. So for example, there on the left, if I have a beaker or a glass of water that's half full at 21 degrees Celsius, that's what we would call 50% RH. If I simply cool that off, let's imagine this, a balloon. You were having a birthday celebration. You blew up the balloons inside the house. That was pretty moist, right? Your breath is pretty moist. There's no condensation inside the balloon. But if you take that balloon outside, what happens to the balloon on a cold winter's day? Well, it shrinks because cold air shrinks or gets more dense. And now that moisture that was in that balloon is going to condense. So if you open up the balloon, you'll notice now it's dripping with water. What happened? You changed the temperature. You didn't remove or add any moisture, you changed the temperature. So we always need to keep that in mind. And this number, 10 degrees Celsius, 100% RH, if I take 10 degrees Celsius outside air that's raining, imagine it's 10 degrees Celsius and it's raining. You bring that air in and warm it up. Its new relative humidity is 50%. Oh, it's actually reasonably dry air. Keep that number in mind, 10 degrees Celsius, even when it's raining, starts to give you outdoor air is actually good dry air when I need it. And then I'll flip you to the research that's been done in a lot of cases in First Nations communities, but a lot of research done on molds and indoor air quality starting in 1988. Health Canada survey of 18,000 children, studies done in Wallaceburg, a basement study, a large asthma study that was done in the year 2000. And here's what they found. I'll go to this slide. Here's what they found. There's a link between moisture, home dampness, and molds and the health of children. So we always would say, and you guys know this way too well, we just don't want enough moisture in our houses that would cause that or allow mold, enable mold to grow. So we really would put it that bottom phrase, any type of mold growth in a home should be dealt with. Sorry for the typo. Any type of mold growth in a home should be dealt with. And so the next little conversation is you need to be able to measure humidity. And unfortunately, the humidity sensors are amazingly difficult to get accuracy. All of these humidity sensors there on the right, they're actually all in the same environment. They're inside a humidor, like a sealed box. They're all at 40% RH, and yet they're sitting in an environment that's 40%. But look at the range. They as low as 21% all the way up to, what's that, 51.5%. So I need you to calibrate your hygrometer, and I have a slide on that, so I'm gonna flip to that. Good news here is I get to flip to some slides as I talk. Here's, if you have, and even if you bought a good one, and go ahead and buy a good one, they should be, you probably wouldn't need one at least $30, but you really, on a community scale, you should probably have one that's 100 to 150 bucks at least. And here's how you calibrate it. You take your hygrometer, you put it inside a Ziploc bag with a cup, and the cup has a quarter cup of water in it and half a cup of salt, and you stir it around for about a minute. Put it in the plastic bag, seal it up. And the RH, the relative humidity, should rise to 75% over, well, in fact, you want to watch it. If it moves to 75% in 10 minutes, then you know when you take it into a house that after 10 minutes you can take the reading. If it takes 3 hours for it to get to 75%, you'll know that if you take a humidity sensor into a house, you got to leave it there for 3 hours before you're getting an accurate reading. So just watch that. And if you find your reading low, let's say it only ever gets to 70%, then you'd say, okay, my moisture meter's okay. I just need to know it reads 5% low, would be kind of the goal. So you want to be able to measure moisture in houses. And then back to mold just for a second. Molds are everywhere. And what makes them grow? Well, nutrients. Mold will grow on just about anything. Certain kinds of mold will grow on just about anything. They'll all grow at temperatures that you and I like to live in. Obviously, they grow in oxygen. We can't get rid of that. The only thing we can control with mold is moisture. And it's really about understanding mold is a symptom of moisture. Think of it that way. When I see mold, you don't have a mold problem, you have a moisture problem. And if you find moisture, you'll find the mold. And if it's wet enough for long enough, there's going to be mold, 48 to 72 hours. And it's not because the place isn't clean. It's not because of something they're doing. It's moisture. There's always mold in the air. You'll never get rid of it. I hear people talking about HEPA filters and things that'll kill mold, UV lights. None of that matters. It's about managing moisture. Keep moisture at surfaces. And notice that bottom line. When the relative humidity at the surface is near 60%, you start risking mold. That's when you want to keep the house at 50 to 55 in the summer, certainly basements 50 to 55, because if it gets above 60, not that mold's going to grow right away, but you get into the risk zone. So it's called either the RH, relative humidity, or what's called the water activity, because sometimes the house might be dry, but the surface might be wet. So if you have a wet basement, for example, maybe the relative humidity in the house is 50%, but you're still seeing mold. And you go, well, it's only 50%, but the material itself, what's called the water activity at the surface, is wet enough that'll cause mold. So keep that one in mind. And so the key to mold is keeping surfaces dry, which on the outside means good drainage, keeping materials dry during construction, water managing your foundations, walls, and roofs, and obviously making sure you're avoiding any leaks through your plumbing or HVAC. And if surfaces do get wet, the key is to get them dry quickly. And the clue is this: if it gets wet, it needs to get dry in 48 to 72 hours. That's what you want to think about. in your communities, if something gets wet, there's a leak, a flood, and you go, well, that's can be hard to do. It certainly can be hard to do, but you would like as much as possible. And if it's wetter, if it's wet for more than 48 to 72 hours, then you really need to imagine that, you know, a carpet, for example, is probably going to have to come out. And how do you get them dry? Through ventilation, venting and ventilation, and ultimately dehumidification. My opinion would be every community should have availability of a good commercial dehumidifier, one that you keep in the, you know, administration office or something, so that if a house happen to have a flood, pipe leaks or something, that you're able to run a dehumidifier in there as quickly as possible to get it dry. And back to the concept of we want to achieve that balance, not too wet, not too dry, plus or minus 5%, in summer 50%, in winter 35%, avoiding that condensation. And really, when we think about that, if I'm going to avoid condensation, I got two choices. I can either warm up the surface to get it above the dew point, or I can reduce the relative humidity to get it below the level where we get condensation. And I'm going to do something, you know, somebody's going to say it might be too complicated, but I actually think it's pretty important. When you understand that this is pretty simple physics to get you to understand moisture. This is called a psychometric chart. And on a psychometric chart, notice along the bottom is the temperature. That'd be the temperature, say, of a thermostat in the house. And at 20 degrees Celsius, these long sweepy lines that you see here, these are the relative humidity lines, relative humidity. That's the 20% line, that's the 50% line, that's the 100%. So here's what I've done. I've taken outdoor air at -5 Celsius, which for you guys is a walk in the park for some of you guys, and at 100% RH. So what's happening outside? It's snowing. If it's -5 and it's 100% RH, it's probably snowing outside, or at least it's, you know, foggy, whatever. If I bring that air in and warm it up to 20 degrees Celsius, its new relative humidity is only 19%. That is, outdoor air is nice and dry. So if you have a house that's wet in the wintertime, a really simple answer is to bring in outside air. Now I got to heat it up because I can't bring it in as cold. I bring it in, warm it up, and its new relative humidity is 19%. So one thing about your communities in northern climates, they have in the wintertime really good drying potential. And in fact, you now know the temperature at which you can start to expect drying. Remember that slide before with the beakers of water in them? 10 degrees Celsius. If it's below 10 degrees outside, even if it's raining, that air is actually pretty dry. So you can use ventilation successfully to dry out houses. And if houses are getting too dry, it's typically because either there's too much air leakage or because too much ventilation. And you could turn down the ventilation rate a little bit or make the house tighter. So hopefully that's helpful. I find it's useful. When I learned this, when people said to me, well, I have condensation on my windows, and I said, we just need to create some ventilation. It's not necessarily bad windows or something bad that you're doing, depending on your occupancy, you know, how many people, how often you're showering, and so on. All we need to do is get a little bit of fresh air from outside and warm it up. You guys will know the equipment that you do that with, heat recovery ventilation systems. Heat recovery is nice because I don't have to heat it as much. I'm going to pass it through an HRV, and that's going to it's going to warm up the air as it comes in, which reduces its moisture level. So pretty useful. And so that was sort of our indoor conversation. I don't know if we stopped for questions or not, but that was kind of a quick indoor conversation about managing moisture. You want to keep the relative humidity low enough so you don't have condensation on surfaces. If you do have condensation on surfaces, that means typically it's cold outside. Your best way to solve that is by doing ventilation, air from outside, higher levels of ventilation, or to put in better windows. And that's why I would say in northern communities, if you are building new houses, triple glazed windows so that they're warmer. Okay, I'll just go one last slide here, which is, you know, where does the moisture come from? People are often wondering, where's the moisture come from? It's not typically in the building materials. The building materials themselves only stay wet for maybe a year to 18 months. That is when you build a house, there's moisture coming out of the drywall, out of the wood. That only impacts for the first 18 months or so. Most of the moisture is created by the people, right? 4 people, just 4 people breathing, perspiring, respiring, they're putting 5 liters of moisture into the air each day. Hopefully that's good. Hopefully you don't have humidifiers running in your communities. I guess if that was too dry, it's okay. But things like cooking, washing, that last one is called seasonal desorption. That is, your houses absorb moisture all summer long, and then in the winter start giving it off. Wood absorbs moisture when the relative humidity is high, and then in the fall, when the weather changes, it starts desorption. So that's why you'll sometimes get calls, say in October, November, people say, my windows are sweating. They didn't sweat last winter, but they start sweating in October, November. And it's just that little dry out period. So you would say to them, increase the ventilation for October, November. As the house dries out, maybe you can stop ventilating quite as much. So there's big moisture sources. And of course, if you have more occupants, then you're just compounding that moisture. And again, the answer is, in the winter time at least, is better ventilation. Some might say, could I run a dehumidifier? Well, what does a dehumidifier do? All a dehumidifier does is take warm, moist air, cools it down to below 10 degrees Celsius to drop the moisture of it and out of it, and then give it back to the house. So a dehumidifier is really useful when the air outside is above 10 Celsius. So if you have a moisture problem in the late spring to early fall, run a dehumidifier. But if you have a moisture problem in a house in the winter, then run your ventilation system. It's more efficient, more effective than a dehumidifier actually is. So keep that in mind, please.
Okay.
Yep.
I think we have a question from Corey, I believe. Is that right?
Yeah,
Go ahead.
not really a question, but more, I don't know, information.
Okay.
I've been doing building inspecting for probably 10 years now.
Yep.
And what I've been finding in my community, along with the high moisture, which is the high carbon dioxide levels,
Sure.
low oxygen levels due to wood stoves, lack of ventilation. When I say high carbon dioxide readings, I'm 1,500 parts per million to 2,500 parts per million in most of the homes here. I've seen a couple of homes under 1,000 parts, like 900.
And Corey, what have you learned? What level are you trying? What have you heard that you should try to achieve?
Well, just from researching it, I'm finding like a connection with different diseases. Just from going back into the history, I'll just throw this out there, see what you think.
Yep.
One of the prolonged exposures to high carbon dioxide levels above 1,500 parts per million, first one that come up was Alzheimer's disease.
Really?
So when I did a research on Alzheimer's disease, it really didn't show up to the 80s. I have the mortality trend here for 1979 to 1991. There was a big oil shortage in 1977 on the state side, and Jimmy Carter did the National Energy Act of 1977, and in there, that's when they changed the. It was both Canada, United States, and the UK. They changed the structure of the house all at the same time. I guess there was some sort of oil shortage at that time.
Yeah, it was the energy crunch. So we made houses tighter, we put in more insulation, and we stopped ventilating houses. So Corey, you have this right. I won't comment because I'm not a doctor on the
Yeah, I get it, but
I'm with you on the carbon dioxide. Here's what we know about carbon dioxide. If you have high carbon dioxide levels, you have a lack of ventilation. That's what it comes down to. And here's what we know, for example.
What I'm trying to say is,
yep.
If you look at this number from the CDC, if I don't know if you could see that.
I can't see it because I'm sharing my screen.
What it is that in 1979 there was 857 deaths of Alzheimer's disease.
Right.
In 1991, which is maybe 11 years later, there's 14,000 deaths.
Right.
99% of that is Caucasian.
Right.
There wasn't no Alzheimer's disease on First Nations at that time because we don't follow building code.
Right.
So if you make a building code change, we don't follow it. Maybe 5 to 10 years later, we make that change. We don't have the same building code act as the outside world.
I understand.
So mostly everybody that's listening on a reserve can probably look back in their time and probably in the 80s didn't know anybody with Alzheimer's disease. And there's more diseases with the trend, the same time when they built the houses better.
So I'm okay with this. Rory, if it's okay with you, I'll acknowledge that carbon dioxide levels, high levels of carbon dioxide in a house are not good. The carbon dioxide itself isn't the issue, right? The carbon dioxide, there's guys who live in submarines for their entire military career, naval career, and they live at 8 to 10,000 levels of carbon dioxide, but they also live in air that's really, really clean. That is, they have HEPA filtration and so on, and they try to ventilate those subs or make new air. But in your houses, I think it's absolutely fair to say, I'm glad you're measuring carbon dioxide. That's a really good indication that your houses are not ventilated correctly. And the answer, the same thing we do in your schools, is you ventilate at the rate of 15 to 20 cubic feet per minute per person. So your houses, if you have 8 people living in a house, 8 times 20, 160 cubic feet per minute. You're quite right. The building code, National Building Code would say, well, it's only a 4-bedroom house. It only needs 75 CFM ventilation. But you would say, no, we have 4 bedrooms, but we have 8 people. I need the ventilation to match not the number of bedrooms, but the number of people in your houses. So your heat recovery ventilation system should have a higher capacity. And you will see, Corey, by all means, try this. If take a house where it's 1,500, go check the ventilation system, measure it, and bump it up to 15 to 20 cubic feet per minute per person living in the house, and you'll find within 24 hours that carbon dioxide levels will be back down to under 1,000, in that 800 range, which is kind of your goal. The outside range is 350 to 450, depending on where you are in the country. Outside levels are 350 to 450, sometimes a little higher, urban centers. But in houses, we'd like to be 600 to 800. And I can give you an example. My own house, there's only 2 of us living in the house right now. It's 2,200 square foot house. But if I turn my ventilation system off, I live in a really tight house. If I turn my ventilation system off, even for a day, carbon dioxide levels in my bedroom get to 12 to 1,400. My wife notices it. She goes, well, it's stuffy in here. And so and it's not the carbon dioxide that we're worried about. It's the other pollutants. So I don't know the medical between carbon dioxide and Alzheimer's. Don't know if that's there, but we do know carbon dioxide isn't good, and you're going to solve it with ventilation. Hopefully that helps. I probably need to move on, and Corey, we can take this up in the question and answer period at the end, but I'll move off of that if that's okay with you.
Yeah, that's fine. It's just 80% of our homes don't have the ventilation.
Well, they do have windows though, right?
Yeah.
So we used to ventilate with windows.
Yep.
When Jimmy Carter and Canada and UK, they said close your windows. That was the big mistake. It wasn't that we started making them tighter. It wasn't because we started adding insulation. It's because we stopped ventilating. And everybody on this call, well, I'm going to say I'm old enough to remember me. I don't know how old you are. I can't see you, but my mom used to come in and open my window, open my brother's window, and said, we're just going to leave that open all night. So ventilation nothing wrong with ventilating by windows. So take that house at 1,500 carbon dioxide levels and just say to the occupants, look, just for the next 2 days, we're going to leave some windows open here. Not all the way. Each window open an inch, inch and a half, 2 inch, something like that. And you're going to find the carbon dioxide levels are going to come down nicely. So you might not have mechanical ventilation, but you do have windows. And you go, but that costs me money to run that. Fair enough. Yeah. I don't want to open the windows when it's really cold, and you guys are spending, big money on oil in northern communities and so on. I get that. That's why you're going to move towards mechanical ventilation, HRVs, and so on. So hopefully that helps. Am I okay to move on? My problem is I can't see you guys, so I don't know if it's.
I noticed Nina doesn't have her mic. Did you want to ask a question, or? If not, I think we're good. All right, go ahead, Gord.
Okay, great. Thank you. And then, now I want to move on to more of the building, if you will, not necessarily inside, but moisture damage of buildings. And we need to remind ourselves, moisture in liquid form destroys buildings, rots them out real quick. And we've changed wetting, and we have less drying potential. So, of course, in terms of moisture sources, you see it there in the screen: rain, snow, humid weather, seasonal cycles. Then you have the people, showers, baths, pets, so on. And then you actually have building-related moisture like construction materials, grading, poor drainage, roof design, those kinds of things. So we need to worry about those. And in terms of moisture flow, it's kind of instructive to know that moisture flows by one of four mechanisms: gravity, no surprise, right? Water runs downhill, but also by capillary flow, water wicking up from the ground through concrete, through wood, up into, it's the way trees work, right? They draw that. And you can imagine a tall tree, 300-foot tree, it has capillary flow of up to 300 feet. That is, water can move up to 300 feet in wood, over 1,000 feet in concrete. The third mechanism is airflow, which is air leakage into wall cavities. And the fourth is vapor diffusion. And we often hear about vapor diffusion, going to put up poly. And it turns out these are in order of priority. The first things you would fix in your community is liquid water flow, gravity, water leaks, roof leaks, window leaks, door leaks. The second thing you would try to solve would be moisture wicking up from the ground. It's actually tough to solve in an existing house, but in new house design, you can stop that capillary flow. The next one that you would try to solve is airflow. You would want to try to stop air leaks, is what you'd want to try to stop. But I want to show you just in a little animation here, it'll show you kind of the four, what we call the 4Ds of water management: deflection, drainage, drying, and durability. Take note of these 4Ds. Houses, we rely on deflection of roof and roof overhangs. Make sure that you have good deflection of water. Get those downspouts away from the foundation. Drag that water away. And if you don't want to use eaves troughs, that's fine. Just make sure down at the grade level that the water drains away from the building. And that includes your siding and cladding systems. The second is to understand good drainage. Remember, I said drainage of that eaves trough. But understand that cladding systems only keep out 90 to 95% of the water. If you've got a wood cladding, if you have a vinyl cladding, doesn't really matter. About 5% of the water actually gets behind the cladding. That's okay as long as I have the ability to let it out, to drain it out. That's why we're going to talk about water resistant barriers. So good grading, good drainage. Third, understand that our buildings have to dry when they do get wet. And because we're living in a northern climate, most of our drying is to the outside. We want our buildings to dry to the outside. So that's why we use products like permeable weather barriers, like a Tyvek water-resistant barrier that's also vapor permeable. It's airtight, it's watertight, but it lets water vapor dry to the outside. So the choices of materials you use are really important. And just to summarize that, the 4 key water management fundamentals in your buildings is to think about deflection. How well is the roof overhangs? How well is the cladding system deflecting water away? Second, how well is the building able to drain? Have I got good grading and drainage away from the building? Is my cladding system built such that if water gets behind it, it can drain out? Third, you think about the dryability. That is, did I use building materials that are able to dry to the outside? And then lastly, you might want to pick more durable materials, pressure treated and so on. But spend your money on deflection, drainage, and then drying. I can't state that enough. Just in the last 3 weeks here, obviously in mainstream community, but in my area, I've been called out to 4 major water leak issues on buildings that are less than 7 years old, and they all came down to improperly flashed windows, no overhangs, that is flat roofs and no overhangs, and poor drainage of the building around the foundation. 90% of moisture issues can be solved by good deflection and good drainage. Good deflection, good drainage. So keep that in mind. I won't even do this one. I'll just go to this one. Foundations is a big issue because I said houses dry to the outside, walls dry to the outside. The problem with basements and crawl spaces is they dry to the inside because you're surrounded by wet soils. In all cases, all soils everywhere are wet. So basements want to dry to the inside. And when we put fiberglass materials, and then our codes, certainly National Building Code and the codes you guys typically build to, would say to you, I need to use poly on the basement wall, that's restricting drying. And so what I'd like to do is talk about strategies for minimizing the effect of moisture problems in basements and crawl spaces. I know you do a lot of crawl spaces, or at least some of you do crawl spaces. And so we want that foundation to be warm and dry and bright and healthy, because people are using it either as living space or they're using it to store items. So we want to keep it warmer. So basements and crawl spaces have these huge technical challenges. You got all these moisture sources. You got the soil dampness, which is the most important. Then you have the water runoff. Then you have construction moisture. And then you also have summer condensation. And I want you to imagine this. You take warm, humid day, warm, moist air. It migrates into the crawl space or into the basement. Warm, moist air getting into a place that's cool. Why is that place cool? Because it's surrounded by cool soils. So by definition, basements are colder than upstairs. And if I take warm, moist air and bring it into a cold space, what does it do? Like that balloon, it contracts and the relative humidity goes up. So basements are wet partly or damp, partly because they're surrounded by damp surfaces, but more importantly, or as importantly, they're surrounded by cold surfaces, not damp surfaces, but cold surfaces, which means basements are higher relative humidity. I know, for example, if you take 23 degrees Celsius air, 23 Celsius, 24 Celsius, in that range, at a nice, healthy 50% RH, that's what's upstairs. And all you do is take that air and put it in the basement, which it's going to do, right? The basement door is open or the crawl space hatch is open. If you take that air at 24 degrees Celsius, 50% RH, take it down to the basement and now or crawl space, and the basement is 20 or 21 degrees, its relative humidity rises to 62%. In other words, it's in the risk zone, not because you added moisture, but because you change the temperature. So every time you change the temperature, it changes the relative humidity. So what do we do if we're going to have basements, crawl spaces? You need to do a better job of moisture control. And we would say, make sure your grading is right. I have solved most basement issues in my career simply by going to the house, putting a string level out from the house, and making sure that the grading and drainage is taking the water away from the building. And you want it away 4 to 6 feet minimum, 4 to 6 feet away. So that's addressing the grading or digging in a swale or running downspouts out further. And again, I know in some areas, because of fall leaf loads and snow loads, eaves troughs are a problem, right? Because they just get iced up. So some communities have said, I don't want an eaves trough. I'm okay with that as long as the drip line, so think about where the water drips to, down at that level, then you would want to put like a river rock or stone or something and grade it away so that moisture gets taken away. Now you don't need to worry about the maintenance of an eaves trough, but you still get good grading or drainage away from the building. And then we would say in new construction, insulate as late as possible. I know some of you are talking new and some existing. You'd want to insulate as late as possible in the process so it gives the basement time to dry. And then you would use moisture barriers underneath the slab. So if you're pouring a slab in your communities, before you pour that slab, you'd put down a really good vapor barrier, poly vapor barrier. And you are going to have to recognize the need for dehumidifiers. Sometimes you just can't avoid the need for a dehumidifier in an existing house. Again, whenever the temperature is warmer than 10 degrees Celsius outside, you need to dehumidify your basements. So hopefully that helps a little bit. And I just want to show you what I want to show you. Okay, if you're building new, or even if you were in an existing house, you could put a drainage layer up that really minimizes the amount of moisture that comes through that wall. So that's a product called Delta. It's a dimpled drainage layer. think I have a, yeah, I'll just show it here. Just play it for you. You know, you would put in your drainage system and then this roll out this dimpled drainage layer on the outside of the basement wall. This resolves, I would say, 40 to 50% of basement moisture issues. Now, in an existing house, is it worth it to dig up? You'd have to think about that. First, start with good grading and drainage, but ultimately, this is a good solution for stopping moisture intrusion in basement. So, just want to give you a little shot of that, of how that works. This obviously is going to get buried now. It's got a little starter strip to make sure dirt doesn't get in behind it. Go around it. If you have a window, egress window in the basement, but just going to show you the backfilling just to finish that off. There you have it. So that stops a lot of moisture issues. And then I would say to you, I already mentioned to you that, you know, if you put fibers on the inside of a basement wall, you're going to have moisture issues. The one on the right is a new type of vapor barrier. It's called Smart Poly. It isn't actually a poly at all. It's a vinyl product, but it has the ability to dry to the inside. So if you have fibers in your basement and you're collecting water in that fibers, then this Smart Poly might be a good choice. What I want to show you is other northern climates. In Minnesota, for example, they do not insulate on the inside of basements. They insulate on the outside of basements. So a new construction, or if you're digging up an old foundation, insulating on the outside is actually a really good choice. It means you don't need to worry about inside and materials getting wet and damaged. You know, some would say just paint the walls white. It's a really nice durable surface on the inside. Depending, obviously, if they wanted as true living space, bedrooms and so on, okay, maybe they want it more aesthetically pleasing, in which case you could finish it. But in many cases, just insulating the outside. The big issue is always that above grade portion. You know, what do I do with that to make sure it doesn't get damaged by lawnmowers or whatever? And we would say there are some good coverings out there. The ICF guys, Insulated Concrete Form guys, have a really good cementatious parge coating, or there's actual cement board products that can go on that outside. And this basement now becomes far less prone to moisture problems. It'd be a good solution for you guys in your communities. And then I wanted to, because we don't have a lot of time left. I know I was late starting. I don't mind going late. We have about 9 minutes late. I just wanted to show you, remember I talked about that condensation issues in walls. I want to remind you of this, that as we started insulating walls, this is in Fahrenheit because it comes from the US, 70 degrees Fahrenheit, if it's 30% RH inside, the dew point of that air is 37 degrees. So if any warm, moist air from the house gets into an attic, gets into a wall cavity, and hits a surface that's below 37 degrees, you're going to have condensation, which means whenever you insulate, you have a chance of condensation. You have two ways of getting rid of that condensation. One, make the wall more airtight, or two, put on an insulated sheathing on the outside, insulation to the outside of the building. So that's the direction new housing is going, is let's make them tighter so we don't have condensation inside our wall cavities, and let's put insulated sheathing on the outside to avoid that to avoid any condensation inside the surface. So it's a little bit odd because Corey's going, well, we started insulating buildings and that caused a problem. And he's right, except we've learned what that problem is. You cannot insulate until you first make it airtight. And you can't make it airtight until you plan for ventilation. And if you're going to ventilate, you're going to say, well, then why bother making it airtight? To some extent, you're right. But all we would say is, but go to mechanical ventilation like HRV. But even small windows, it still makes sense to make the building airtight. And when you have to, open the window for short periods of time. There's nothing wrong with that. It's still a net energy benefit. The walls are warmer. But you do not want condensation on surfaces, say in windows, and you certainly don't want condensation in wall cavities. You have two choices. Block the holes, make it airtight, or add insulation to the outside. And so what you need to know in both new and existing buildings, if you're retrofitting, as you know, Canada's talking about retrofitting buildings, one of the best things you guys could do is to take off the siding, the cladding system on the outside, and add insulation. Simultaneously, you're going to make the building more energy efficient, more comfortable, and you're going to reduce the chance for condensation inside of the wall cavities. The one on the left is that green stuff. That's mineral wool, really good choice, really fire resistant, sound resistant. The one on the right is a foam-based product. Both of those can work, but insulated sheathing is going to be, if you're doing major retrofits of existing houses, you're going to love that. That's a great choice. Then I wanted to chat about, so remember I talked about drainage and deflection. I just want to show you the elements of proper water resistant barrier. So first and foremost, not first and foremost, at the bottom, we want a flashing detail to kick the water away from the wall. 2, this is showing Tyvek, doesn't have to be Tyvek, it's one of the leading brands. Proper button cap fasteners. This is a product that is airtight, vapor permeable, and watertight. And you're going to use it as an air barrier. So if you're recladding your buildings or building new, you would put this on over top of that foam, and you would overlap it. You would tape the joints, and you would use button cap fasteners, and you wrap the house. And this product is simultaneously watertight, airtight. But if moisture does get behind it, it's vapor permeable. It's like a Gore-Tex jacket. It's able to dry. So that's the fundamental elements of a water barrier. But then I want to show you, just get to the window, that wall's great, nothing wrong with that wall, except walls very seldom leak. It's always the penetrations in the walls that leak. It's always the windows, for example. And here's the right way to do a window. Ideally, you would slope the sill. So I always say it's a 10-point scale, rating point of 10 points. You would slope the sill. If you can't slope the sill, that's fine. What you do is you do a back dam. I'll tell you what that is in just a second. Second, you'd use that proper house wrap, proper fasteners. That's point number 2. Point number 3 is the right cut. You do what's called an eye cut, and you fold in the sides. That protects the jambs of the window, but it also keeps the head and the sill clean. The 4th point is you cut the weather-resistant barrier and fold it up so that you can put your window flange underneath that. Number 5 is actually to protect the sill. The interesting part about windows is they leak at the top, but do all their damage at the bottom. And you really want to protect the sill. This happens to be a flexible flashing. There's plastic flashings you can get. And then you caulk, not on the bottom. You caulk on 3 sides to keep out the air and the water. But any water that does get in, you want to let it out. So you don't actually caulk or tape the bottom. And then you tape with proper flashing tapes on the sides and on the head. And notice on the head, we actually skip taped a little bit. So if there is any water above the windows, it doesn't get behind the window. It comes out the front face of the window. So that's the proper installation of window. There's different methods. If you like that animation, there's a free building science website called constructioninstruction.com. And they have about 50 different animations. So from a training perspective, you could show your crews, hey, I want you to install it this way. You can see here, there's no language barriers or anything. And then I want to remind you, in the National Building Code of Canada, it requires, if the window is not protected by an overhang, if the window's not protected by an overhang, then it needs to have a head flashing. And I'll just go to that here. Where was that? I think it's here. I'll just play you this one. I want to play you this one because it shows the head flashing, and it also shows insulated sheathing. Remember I said you're going to do insulated sheathing? So I just want to show you what a head flashing looks like. And this is always really useful for you guys to do in any of your houses, even if they're protected by overhangs, because some of you are living in really wind-exposed areas. But that's a head flashing. All it is a piece of plastic or bent metal that just makes sure any water coming down the wall, it drips out over the front face of the windows rather than running down the sides and doing damage on the sill. Notice too, in this case, the water resistant barrier actually goes on first. So this would be a classic renovation of a recladding of a house. And you put the foam on after, and then you would strap this with, I'll show you quickly here. We'll just run. Again, it's showing a flashing to keep that water away from the window. But now they're strapping with a 1x3 strapping. This would be a classic reclad for you guys. Take that siding off, put 2 inches of foam, put a weather-resistant barrier, put 2 inches of foam, then strap that wall and reattach the cladding. This wall now has a vented airspace. You are going to want to put a bug screen behind it because depending on, well, I'm going to say I've seen enough black flies and mosquitoes to know you don't want those up in behind. But there's a really good durable wall, a great way to remodel or renovate some of your existing buildings. Just wanted to rehash this. I said proper flashings. The standard tuck tapes are not proper flashings. You want to actually use a 4-inch wide butyl-based flashing product is where we'd like to get to. And then, you want to pick the right house wrap. You want to pick that one that's durable. So we're kind of at an hour. I just wanted to show you this one as well. These are penetration.
We're willing, Gord, I sent a note out to everybody, like, we can continue for a bit, and those that have to leave, we're going to get on top of the recording anyway. So we can continue.
This is about the slides I wanted to show anyway, so I'm not that bad. I'd like to get to questions. This is just showing how you do penetrations. So Tyvek, as an example, has this nice flexible product called Flex Wrap that'll do penetrations. Or this is showing a line set for a heat pump. Wouldn't have to be a line set, but I just want to show you this one. This is a product called Quick Flash that actually has this really nice boot that goes in that stops any water penetration. So some of you are maybe using heat pumps, but think about a dryer vent, think about range hood vent, something like that. These are just ways of making sure those penetrations are done correctly. And so I'll just put up this last slide, and I would say to you, kind of to Corey's point, moisture is a bigger issue than ever before. We've made some changes to houses, and we are going to go back to no insulation in houses, or we're going to have to move forward. If you're going to insulate, you got to make them more airtight, and you got to make them more watertight. And, your community members, I'll call them customers, are looking for answers, and the answers are always deflection and drainage are the most effective. And you're going to see more and more interest, net zero, passive house, all of those programs. You're going to see more and more interested in more insulation. So you have to do a better job of water management details, and it's really all about the details. And the nice part is the incremental cost of proper water management is actually really low. So that was kind of the formal part of the presentation. Sorry I was late getting started, but any questions? I'll stop sharing.
If you, so anybody wants questions, great. I can see everybody on my 49-inch screen here, which is great. So if anybody has questions, put your hand up and unmute. And if not, Claude, you want to go through some of the chat questions here?
Sure.
Sure, I certainly will, but floor is open at the moment. So there's been a number of comments about the reporting. Yes, we do issue the reporting generally within, well, certainly we try our best within a few hours, if not within 24 hours after our webinars. I'm just trying to go through the list here. Is it wrong to do rigid on the inside, then apply a silver vapor barrier on the inside?
That's a great question. I see this. That's been used a number of times. The silver or aluminum foil is acting as the vapor barrier. Nothing wrong with that. All I would say is, fortunately, the outside clad is even colder. So unless it's really airtight, the best is on the outside. But if you do it on the inside, you just need to make sure it's really, really airtight, because I can't allow any warm, moist air to get behind it and through the insulation and hit the cladding. So you typically want to do it from the outside. But you would not want to use foil faced. Ideally, you don't use foil faced on the outside. It's too impermeable. So you want to use a vapor permeable. XPS is more vapor permeable. Rockwool, that Rockwool product's really vapor permeable. If you are going to use foil faced foam on the outside, use enough of it that it's always going to be warm enough that it won't condense. So you want at least 1.5 inches to 2 inches of foil faced on the outside if you're going to do it. Nothing wrong with using it, as long as you put enough out there that it's not going to, it has no chance of condensation.
Okay, we have another thing here regarding HRVs, heat recovery ventilation systems.
Yep.
Certainly, we can see they're certainly beneficial, but short of that, because we are sometimes, I guess, on First Nation communities restricted by cost of things and access to funds to basically help renovate or rehabilitate ventilation issues in a home. Is there any other maybe cost-effective solution to ventilation short of opening windows and doors?
Sure. So, I'm an HRV enthusiast. I designed and built them back in '82 or '84. So, I'm obviously an enthusiast. But I get it. Even back then, we had troubles, with cold climates. Boy, do they freeze up, and maintenance and filters and so on. But the key word is not the heat recovery. The key word is ventilation. Let me see if I can test you. How much ventilation do you need per person? Remember I said if you got 8 people, how much ventilation do you need per person? 15 to 20 minutes. All right. There's absolutely nothing wrong with you guys putting in a good, quiet bathroom fan. Make it quiet because otherwise they won't run it. Make it energy efficient. And there's these great new fans, Panasonic, Throne, Newtone, all of these great fans that'll run, say, CFM, 80 cubic feet per minute, which is good for 4 or 5 people. They draw about 11 watts. In other words, they cost all of about $11 a year to run. But yes, they're taking cold air out. Where's the air coming in? Well, the air's coming in through cracks, holes, so on and so on. Your houses, especially old houses, aren't that tight. The big issue is could the air come down a chimney if you had a wood stove? It's unlikely, but it's possible. So as a community, you would say, you could do a quick blower door test on the house. Hopefully you have access to, but do a quick measurement. Or you put in a fan, try the fan, and just watch and see if the wood stove pops back, like if it depressurizes the house. So you have to be a little careful. It's unlikely that an 80 or 100 CFM bathroom fan would cause a problem, but it's possible. And if it does cause a problem, then rather than opening a window, you put in what's called a makeup air hole. You have a hole, it's a duct, comes say into the basement. It's got a damper on it. You hook it up such that whenever the bathroom fan comes on, the damper is able to open. You don't want a barometric damper just flapping in the breeze. You actually want an electrical damper. And the fan manufacturers make these kits. Get the fan, you interlock it such that whenever the fan goes on, this hole opens up and it allows just a small amount of air into the basement. You don't necessarily need that unless you have a wood stove and it's backdrafting. But I'm going to say to you, from a ventilation, air quality perspective, a good, quiet bathroom fan does every much as same airflow as an HRV. If you have an 80 CFM HRV and an 80 CFM bathroom fan, you get the same benefit of CO2 reduction, moisture reduction, so on. You just don't get the energy recovery. And you have to worry about where's the air coming in. Is it going to be cold or drafty? I'm a huge, this pun intended, I'm a huge fan of fans. I have absolutely, in older houses, you can imagine, even in my community, in older houses, I wouldn't tell somebody in a 100-year-old house to put in an HRV, but I'd be the first one to say, put in a bathroom fan. And I said it to my brother. My brother's got an old house, 110 years old. What's changed? He's got pets. He's got more moisture. He's got a home office. His kids are home all the time. He needs a ventilation system. His carbon dioxide levels are too high, even though he lives in a leaky house. So, Jim, don't put in an HRV. Put in a good, quiet bathroom fan. And that's what we did. And we didn't necessarily run it all the time because your residents, your occupants, your community members are going to say, well, that's going to waste energy. Let's just run it enough that I have reasonable air quality. How would I judge? Corey CO2 or moisture levels. If I don't have condensation on windows, I don't need to run the fan as much. So typically what we do is put that fan on a timer, and the timer runs 4 hours in the morning, 4 hours in the afternoon. Did that solve it? Yep. It didn't solve it? 6 hours in the morning, 6 hours in the afternoon, and find the sweet spot that gets rid of the moisture and doesn't cost an arm and a leg to run. So that was a long answer to a relatively short question, but I'm pretty passionate. I'm very passionate about it, guys. You think about the cost of a bathroom fan. That's not that tough to install. You guys can do that, and you could solve a lot of moisture problems by doing that.
That's a great answer, because I'm sure with the funding and challenges financially, it's reasonably affordable. Peter asked a question about building code, saying that certainly ventilation systems are required by code, but quite often we have to consider, in a number, or a good number of First Nation communities, certainly they're not always building to, we'll call, the building codes. So I guess the common sense approach, if there is such a thing as common sense, because sometimes you wonder, we need to think about what you say, ventilation, and certainly how do we reduce moisture out of the house for the most part. So any more comments maybe about building codes? Are they headed in the right direction? Maybe not.
Yeah, I actually was just doing a little piece on this, the historical side of building codes. The first building code in Canada was published in 1941, and it didn't have any insulation, no requirements for insulation, but it actually had requirements for ventilation in 1941. And it was under the health and safety side of the code. And it said the code was mostly about structure and fire safety, but then there was this section on health and sanitation, and it said you needed proper sewage facilities, and then it said you need ventilation in bathrooms and kitchens, and that ventilation was windows. You needed to have a window in every bathroom and every kitchen, or you need to put in a fan. That was 1941. In 1990, the building code changed and said, you need to put in air barriers. You need to have an air barrier in your house. And now you need the capacity for continuous ventilation. So they not went away from windows. They said, in addition to windows, you need to put in mechanical ventilation, as simple as a bathroom fan. And it's right in the appendices of the code that says the reason we're doing this is not for energy efficiency, doesn't have to be an HRV. We're doing this for health and safety. And I would ask you this, if you asked any one of your community members, when would you like fresh air in their home? They would say, well, I always want fresh air. I always want healthy, fresh air. Right. How are you getting it now? Well, geez, I don't want to open my windows. It's cold. There's bugs. Maybe there's dust at certain times of the year. So how are you getting your ventilation? Because we used to ventilate by opening windows. It's not that we're building houses too tight. It's that we stopped opening windows. And every community would have known back in the 40s, 50s, 60s, 70s, you got to crack a window. You're going to run that wood stove, you got to crack a window. And now for a whole bunch of reasons, again, energy costs and dust and cold and so on, then we think, well, we're not going to ventilate. But you need the capacity. Here's the word, capacity for continuous mechanical ventilation. Not because it's code, but because your residents deserve, your community members deserve fresh air.
Gord, before we close off, I'd like to take a minute, or you to take a minute, and tell us about those educational programs that you offer. And certainly I've been onto your website, and I see a lot of great information out there for just about anybody on not just building science and moisture, but many issues facing housing.
Well, thank you. So I have a group of partners in the U.S. called Construction and Introduction. We, the three of us, Mark, Justin, and I have been traveling for years to communities. I've traveled to many First Nations groups, some of the most rewarding work I've done, but we've been traveling for decades. Before COVID came, we were kind of tired of traveling, so we created a facility, a learning center in Denver, which is a handheld facility, and we imagined that people would come to us. And in that facility, you actually build a wall and then water test it, put in a mechanical system and then air test it, and so on. So we created this, we call it the CI Live Experience Center. Of course, COVID came and nobody can travel to us, so now we're filming. So recently, for example, Justin, my partner, showed a wall that he built with basically the way walls are built in Southern Ontario. I said, hey, Justin, could you build a wall? And here was the wall. OSB with tape, red tape around the window and building paper. And so Justin built that wall, and then he put it on a spray rack, put water on it, and it leaked within 3 minutes. 3 minutes it took for water to get through that tape and the OSB and the building paper. And so I'm going to encourage you, go to Construction Instruction, sign up for the newsletter, get the app. It goes on your phone or iPad, and you can follow that. And then in addition, at Building Knowledge Canada, we've been very pleased to work with Enbridge Gas and others who ask us to do webinars on a regular basis. So if you follow us at Building Knowledge, you'll find I'm doing a long session, similar session, a bit longer, about 3 weeks from now for Canadian Home Builders Association on moisture and moisture management. You're going to see some of the same slides, obviously. You guys have a bit of a pre-look at it. But so, yes, either buildingknowledge.ca or constructioninstruction.com. And thanks, John, for allowing me to plug those two.
No, I've been, we've been actually talking about among our membership of trying how to get access. So, for example, what we talked about is having you go to, a hub of, like, for example, Saskatoon, and then we bring in a number of people within that zone, right, for a couple of day sessions. That's sort of what we've been sort of envisioning as well once COVID lifts. And what we would do is that, those that have participated on all these webinars would be first come, first serve. They would get the invites, obviously, too. So that's sort of what we've been thinking, because of, I'm not a big fan of conferences, because I think that they're a waste, but hands-on practical instruction type of web seminars is sort of, complements what we're doing here. So I think it's great.
And I'm looking for any excuse to get back to Saskatoon. I lived there for 5 years. My kids were born there, so I always like going back to Saskatoon. So.
Yep, great area. So we have a number of other questions. So what we could do, Gord, if you're okay, we're just send an email link to everybody as well. If they have any questions, they can reach out to you directly.
Yep. Yeah, absolutely.
And then we also have you doing a couple other ones for the next few days. So you'll be appearing on, I believe, 3 other webinars for us. So,
and I'll be more organized.
Well, hopefully we'll get the technical stuff worked out. So anyway, it's 2:16. Unless there's any really quick question, if anybody. If not, we can shut her down there. Christopher, you look quite content there on the chair. Yep. Okay. All right. If not, thanks everyone, and we will send out the emails and extra information from Gord, and we're send out the link for Tuesday. So
thanks, guys. Appreciate your patience. It was good of you.
All right. Thanks, everyone.
Okay. Take care.